Another special type of address is the local loopback address, which is very useful for testing. A device can send a message to itself, and this helps verify or make sure that the TCP/IP stack is installed correctly on that machine. A typical loopback IP address is 127.0.0.1. But remember please that anything in the 127 range is deemed a loopback address. This is often seen as one of the big mistakes by the designers of IP version 4. A 127 address is a Class A address. Class A addresses have 16 million odd host addresses, and by choosing this address range for the loopback address, we lost the use of potentially 16 million IP addresses. Those addresses cannot be allocated as public IP addresses on the internet, thus making the IP version 4 address space smaller than it may have been. In IP version 6, a different address is used for the loopback, ::1, and they made sure that they didn't make the same mistake again. So here's an example. I can type ipconfig on my PC, and this will give me the IP address of my machine. In this example, it's 10.0.0.6. That's the local IP version 4 address on my PC. So I could ping 10.0.0.6, and as you can see, the ping succeeds. I can also, however, ping my loopback address. So I could ping 127.0.0.1, and notice the ping also succeeds. But don't forget, anything in this range is supported. So 127.127.127.127 is also a loopback address. What about 127.1.2.3? It also works. So anything in the range 127.x.x.x is also a loopback address, and any one of those addresses could be used to test the TCP/IP stack. Now this machine has both IP version 4 and IP version 6 installed. So here's my PC's IP version 6 address. So I could ping 2001:20::2, which is my local PC's IP address, but I could also ping ::1, which is my IP version 6 loopback address. Now this video doesn't discuss IP version 6 in any detail, but it's worth pointing out that we have both an IP version 4 loopback, such as 127.0.0.1, as well as an IP version 6 loopback, such as ::1. IP version 6 addresses are not wasted, or to be more politically correct, IP version 6 addresses are optimized more than they are in IP version 4. Please also note that routers and switches also have loopback addresses, and that's not the same concept as the loopback address that we're discussing here. So be aware that in the field, or in the real world, engineers will often refer to a router's loopback address, and that's not the same as what we're discussing here. You've got the local loopback, which is the Class A address, 127.0.0.1, but routers and switches can also be configured with valid IP addresses on what's called a loopback interface. So a router or switch may have a loopback interface, such as interface loopback 0, configured with an IP address of 10.1.1.1/32. So in other words, we have a Class A address, 10.1.1.1, with a /32 mask configured on a loopback interface. But network engineers may refer to the router's loopback IP address, and they are referring to this IP address and not 127.0.0.1. I will explain, as I've mentioned in a moment, what a network mask does, but what I'd like to point out here is that routers and switches have separate loopback addresses which are different to the local loopback address that we're discussing now. Routers and switches do support the loopback address of 127.x.x.x, which allows us to verify the TCP/IP stack, but loopback interfaces on routers and switches are very useful for other things and are used by routing protocols such as OSPF. Now, RFCs, or Request for Comments, are formal documents from the IETF, or Internet Engineering Task Force, which are typically drafted via a committee from multiple vendors and are reviewed by interested parties. RFCs are intended to become Internet standards, and the final version of an RFC will become an Internet standard, and thereafter no changes are permitted to that RFC. However, changes or updates can be made in subsequent RFCs, and you'll often find this where certain RFCs are superseded by other, newer RFCs and therefore become obsolete. Essentially, a lot of the information that we're studying in networking comes originally from RFCs or Request for Comments. They are important to understand and read if you want to get into the nitty-gritty or details of specific protocols. However, in networking, one of the jokes you may hear is that if you can't sleep at night, go and read a bunch of RFCs, and that's going to put you to sleep. However, some RFCs are actually done in good humor, and there's even an RFC 1149, describing IP over avian carriers, or in other words, how to transmit IP packets using pigeons. And I'm not joking, go and have a look at RFC 1149, and you can see how it's possible to send data using pigeons. Obviously done in good humor. Now, being serious for a moment, one of the famous RFCs that you need to know is RFC 1918. RFC 1918 discusses private IP addresses, which are non-routable addresses on the Internet. These addresses will be blocked by Internet Service Providers, or ISPs, and can thus not be used for sending traffic onto the Internet. So here's RFC 1918. Just do a simple search in Google or your favorite search engine, and you'll be able to find this RFC, or go to tools.ietf.org/html/RFC 1918. As you can see here, various parties were involved in the drafting of this RFC, and it also obsoletes previous RFCs. This RFC is address allocation for private internets and explains best practices for the Internet community with regards to private addressing. Notice the date, February 1996. That's a long time ago. Even that many years ago, it was recognized that there was a problem with the exhaustion of IP version 4 addresses. As I'm recording this in 2015, the address registrar for the Americas has recently run out of IP addresses. So this RFC was created to try and increase the longevity of IP version 4, and it's actually worked quite well. The exhaustion of IP version 4 has been postponed for longer than a lot of people expected. In this RFC, they mention some of the problems of the Internet, which are still challenges today. For example, how the Internet has grown beyond anyone's expectations. And this RFC describes the use of private IP addresses internally within organizations, and those IP addresses would be NATed or address translated when traffic is sent onto the Internet. Notice in the RFC it states that the Internet Assigned Numbers Authority, or IANA, has reserved the following blocks of IP address space for private internets. So we have network 10, which is a Class A address, networks 172.16 up to 172.31, which are Class B networks, and 192.168 all the way up to 192.168.255, which are Class C networks. They refer to CIDR or CIDR in the RFC, and we'll discuss CIDR in a moment, and I'll explain what these masks mean, but essentially notice that a single Class A network, 16 contiguous Class B networks, and 256 Class C networks have been allocated for private addresses. So once again, RFC 1918 discusses IP addresses that are not routable on the internet. There are 3 blocks of addresses, 1 Class A network, 16 Class B networks, and 256 Class C networks. Here are the range of addresses once again, and remember, when you are sending traffic internally from an IP address such as 10.1.1.1 to a website such as google.com or facebook.com, your IP address has to be NATed or network address translated to a public IP address such as 15.1.1.1. This is a public Class A address, and this is a private Class A address. These addresses will not be accepted by internet service providers and therefore will not be routed onto the internet, unless, of course, an internet service provider forgot to add an access list blocking traffic from these networks. So in this example, my PC has an IP address of 10.0.0.6. That is a private IP address which is not routable on the internet, but I am able to ping yahoo.com, which has a public IP address of 87.248.122.122, and that's because my IP address is being NATed or network address translated by my router when I send traffic to the internet. Here's another example. Ping google.com. The pings succeed because once again my IP address is being NATed. NAT is not covered in this video. Please refer to other videos for explanations of network address translation. But in brief, NAT will translate one of these IP addresses to a publicly routable address when traversing a router. That's how I'm able to use a private IP address on my local PC but still be able to access devices on the internet. My address is being NATed when I traverse my local internet gateway, which could be as simple as your router at home which connects you to the internet. The next special IP address range is the IP version 4 link local addresses, or more formally, dynamic configuration of IP version 4 link local addresses as per RFC 3927. Microsoft referred to this address order configuration method as automatic private IP address, or API-PA, so that's Microsoft's IP version 4 link local addresses. Now this is used where a PC is configured for DHCP, or Dynamic Host Configuration Protocol, but no DHCP servers are available. So an IP address cannot be allocated via DHCP, and therefore the PC automatically chooses an IP address in the range 169.254.0.0. This allows computers to use link local IP addresses for communication on a local segment. Now, in the really old days of networking, going back to Windows 3.1, if you wanted 2 PCs to communicate, you had to either allocate an address using DHCP, or you had to manually configure the IP addresses on the PCs to communicate with each other. These days, that's not necessary, because IP version 4 link local addresses will allow 2 computers to communicate with each other when no DHCP server is available. So if you connected 2 PCs back to back using a cable, they'd be able to communicate with each other without the user having to configure static IP addresses on those devices. The PCs would simply use an IP address in this range and be able to communicate with each other. Hosts randomly generate the host-specific portion of the address. This is a Class B address. Notice the mask 255.255.0.0, which indicates that the first 2 octets is a network, and hosts will randomly choose the host-specific portion of the address. Once again, this makes the lives of non-technical users a lot easier because they can simply connect 2 devices together without the need of a DHCP server allocating addresses. The 2 PCs can immediately communicate with one another. The user doesn't have to configure a DHCP server or manually configure IP addresses on the PCs. As long as the 2 PCs are connected via a cable or a local segment through a switch as an example, they can communicate using IP. So a PC with IP address 169.254.1.1 can communicate with another PC which, for example, chose an IP address of 169.254.1.2. No manual configuration is required. In this example, I'm using consecutive addresses, but typically the addresses chosen by the hosts are random and won't be sequential like in this example. Be careful, however, with this address range. It's non-routable. In other words, the hosts can communicate on the local link, but their traffic is non-routable. This can cause issues because users will be able to communicate with other devices on the local segment or local link, but they will not be able to communicate with devices on the internet or devices in a different subnet. So if you type ipconfig on a PC, for example, and you see that the PC has an address in the range 169.254.x.x, that means the PC was not able to get an IP address via DHCP and dynamically allocated itself an IP version 4 link local address. No DHCP server was available, and thus an IP address wasn't allocated to the device. It simply chose an address from the 169.254 address range.